Then we'll move on to the new sections, less and less independent material properties. Any questions before I erase those? Should be straightforward, right? Basically, that's your roadmap. So here is a new section. I believe right now we have done is this okay, transverse. Okay, so what we have done is the isotropic, and before that is the end isotropic. Okay. So for an isotropic material, we know we have 21 independent material properties. And down to here, we know that's a line, right, for three-dimensional, most general. And then for here, I want to show you today only 5, okay? Only 5 independent material properties. So first one, let me introduce what TRL is. B, transverse. Transverse, sorry, V-E-R-S-E, transverse, okay. What means transverse, transversely isotropic? So, drawing is a little bit challenging. Okay, for example, if I lay down the fibers, okay, I lay the fibers in the vertical directions. And for some reason, the fiber is not uniform. For example, the fiber is kind of cone-like. Okay, I periodically label and place the fiber in the uniform pattern, and then the remaining space I filled up with resin. So basically, this is a fiber. I exaggerate. Okay. And this is 1 unit of the fiber, and assuming that's very long in one direction. So I kind of aligned, kind of placed in the pattern. So rather I want to build up an array of the pattern for placing this one. So next one will be something like here. The other one is the same. Okay, those are the fibers. And then the next one will be the same. Okay, something like this. So you see my intent. I try to build up a pattern. Something like this one. Okay. So if I repeat this kind of building, basically you can see I'm trying is I keep the same pitch. I keep this L the same for X and Y directions. Okay, for example, this is the X direction and this is the Y direction. So basically the pitch of placing this kind of fiber are constant in X, Y directions. Okay. But in Z direction, basically you can see, for example, at the bottom, X, Y, Z. At the bottom level, let me try to get a cross section at the bottom level. At the bottom level, so for example, due to these sections, and to cut this one, then the cut it would be, the area would be like this. You know what I'm saying, okay? You don't need to kind of mess up your drawing, but that is my intent here. Okay, due to the cut of this level, we have such 5 sections. if I move this cutting plate upward, you can see the cutted cross-sectional area will be smaller. But in this way, for each sections, for each okay, on each of the XY plane cuts, the again, this is a fiber, and then I said the space between fiber is filled up with thicker material, for example, polymer or resins. So basically, this form is this. The material is something like this in that XY plane. It's something like this. This is the fiber, and those ones are filled up with the epoxy. So basically, here, for example, okay, something like this. So for this material, sometimes we call this one a cross-section of the fiber. It's called a feeder. And for the space filled up with epoxy, basically we call the matrix. Okay. For this kind of things, basically we call it two-phase material. Okay, usually we give the name like this. Okay, so for each section, this two-phase material basically is isotropic. That is our assumption. For this simple drawing, I couldn't mimic exactly the isotropic, but just to demonstrate the concept, in this plane, in XY plane, equivalently, the whole material is isotropic. Okay, this is for example, let me say this is a level 1. This is a level 1. If we move the level up, you can see the feeders, the volume fraction, well, the area fraction of the feeder will getting smaller, right? Because the top here, the topper is getting narrower. So for the level 2, the higher level, so for higher level, the feeder could be something like this, smaller. Okay, but in terms of the pattern here, that still be isotropic, but the difference is the area fractions of this upper level is smaller than this one. So although they are isotropic, but in terms of the example epoxy and using respect to the fiber, then this one could have a softer, this could be softer or more compliant, this could be rigid or stiff compared to isotropic. Okay. So such an example is termed as we classify as called the transversely isotropic. Isotropic is in terms of XY plane, and transverse, that means that we transverse in the Z directions. The isotropy is changing. Isotropy is changing over the Z directions. I would say the value, not the value. How to describe this one? I kind of just utilize my word. So from here, for example, for isotropic material, we know that we can utilize its Young's modulus and Poisson ratio, and the two will be sufficient to describe. For example, this one will be the value at the level 1. And for example, the Young's modulus and Poisson ratio at the higher level, for example, level 2. Okay. And those one, only 2 parameters will be sufficient to identify the parameter for the isotropic material. But individually, this value won't be the same as the higher level. So that's what I mean, the transverse. The properties, isotropic properties keep retained, but in terms of the numbers for individual parameters, changing over the z-axis. So that is the meaning of the transverse. Okay. So that's the definition here. And then here I want to see how can we start from here to simplify from 9 to 5, and by knocking out 4 more independent material properties here. Okay, so that is the learning goal for this section. Again, we can begin to think about what means the material symmetry. Material symmetry basically is saying the relation between the stress and strain are constant. Doesn't matter which orientation of the, doesn't matter which coordinate system we pick. Okay, we stick with this one. So again, for our, we have the, say, for example, tau ij and epsilon ij are the described in, for example, XYZ coordinate system, okay? And then tau ij prime and epsilon ij prime are described in, for example, a new coordinate system. Okay. And then between the old coordinate system and the new coordinate system, we know we have certain transformation tables. Okay. And again, we pretty much follow the same procedures. Once we build out these transformation tables, then we proceed the procedures in what we have done before, and then we simply compare the Hooke's law or compliance metrics in this coordinate system and in this coordinate systems. Okay. So now we want to build up this transformation type. Okay, we want to build up this one. And what is this content? Again, right now we're looking for is isotropic in XY directions. So for example here, in which, let's say, the Z or Z prime directions is our transverse directions. Okay, so let me define this kind of Z direction as our transverse, and let me say the XY is our isotropic plane. So now, what is the definition of the isotropy? The isotropy is a very specific material symmetry in the way, listen this carefully, the material to be isotropic, it has a very good material symmetry. The point of the symmetry is this. Basically, doesn't matter the orientation of the transformations, the material constant won't change. And let me use one counter example to explain this. Before, when we talk about the isotropic material, when we talk about this, we call the materials is constant on the pair of the points, that is the mirrors reflected about one plane. For example, let me pick this plane. This is a plane of symmetry. And for example, here we have, say, x, y, z. So here we have a point x, y, z, and this we have a point x minus y and z. The 2 points are mirror symmetric with respect to this plane. And we call the material as isotropic at these points. They have the same material constants at the 2 points. We call it isotropic. Okay, isotropic, that means the material properties is symmetric with respect to a plane. Then isotropic in the xy plane is this. say this is our original material. And say let me find the orientation of this material with respect to origin. So let me call it theta. Then for this material, I do the rotation with respect to the origin. So basically rotation happens on the circle. This point move to here, and that will be the different, let me call this the theta 1, and this is theta 2. Okay. To the isotropic, the material properties at this point equal to those at this point. And even at any point, as long as you keep the rotation transformation regardless the value of the theta, the material constants basically change over, material properties keep constant along this kind of transformation. Okay, so which means here I want to build up the table. For example, let me say this is x prime and this is y prime. The between x prime y prime relation is defined by theta. So the transformation table can build up is this. This is cosine theta, and this is sine theta 0, 0, 1, and minus sine theta cosine theta 0, 0, 1. Okay, to be simplified, I want to use this kind of the brief writing. C means cosine, S means sine. Okay, C S minus SC 0, 0, 1, 0, 0. I simply use C for cosine and S for sine. Okay, set writing. So the material is isotropic. That means for all possible values of theta, the material properties like Young's modulus, like Poisson ratio. Okay, a constant. So that's the definition. So which means before we only apply a pair of the point with respect to one plane of a symmetry, then we repeat this twice more, 2 more times into the 2 other different orthogonal planes. Then we come up with the description of the isotropic 9 independent material properties. For isotropic, for all the possible values of the theta, for example, you start from theta equal to 0 degrees, 1 degree, 2 degrees, etc. Repeating what we have done, then compare all the things, then you will be able to eventually, possibly, you will reach these conclusions. And this can be assigned as a project, okay? But this project won't, can be very good for beginners, but here let me give you another better way to do it. Okay. So a better way to do it, I will demonstrate here in this class, is this. We start from here, then let me erase this one and give more space to talk about this. So right now what I'm going to do is this, to find out the contents of the relation between stress and strain. So we start from here. Right now we already have the transformation table. We can accordingly find out the relation between the stress or between the strain. And then given relation in one coordinate, from there we can find the relation in the other coordinate. The roadmap just the same as we done in the previous sections, 2-dimensional isotropic material, the same roadmap. Okay, the thinking is this. So let me define this matrix. Is L, okay, and the L is the same symbol we used before the transformation matrix. So that means the tau x prime and tau iz prime equal to tau iz. Here we apply transformation of the stress and L transpose. Again, that is the formula we've been talk about before. So this one, let me implement this in detail. So that is a C as 0 minus 0, 0, 0, 1. Okay, and here tau, let me expand it in xy direction. Sorry, here I use 1, 2 for xy, 1, 2, 3 for xyz. Okay, so 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, and 3, 1, 3, 2, 3, 3. And here is L, so C as minus 0, 0, C, 1, 0, 0. Okay, transpose. For this one, I have applied transpose of this L, so you can see that minus come to up there. Implement this. Don't write. Just be patient with me, okay? C squared, tau 1, 1, plus CS tau 2, 1, plus CS tau 1, 2, plus S squared tau 2, 2. That is the first element. The second element minus CS tau 1, 1, minus S squared tau 2, 1, plus C squared tau 1, 2, plus CS tau 2, 2. Second element. The third one, C tau 1, 3, plus S tau 2, 3. Then for the second one, minus C as tau 1, 1, plus C squared tau 2, 1, minus S squared tau 1, 2, plus CS and tau 2, 2. And basically that should be symmetric. Okay. So this one is S squared tau 1, 1, minus SC tau 2, 1, minus SC tau 1, 2, plus C squared tau 2, 2. And this is minus S tau 1, 3, plus C tau 2, 3. The last one will be easy. C tau 3, 1, plus S tau 3, 2. The first element minus S tau 1, 3, plus tau C 3, 2, and then tau 3, 3. Okay. So similarly for strength component. So that means the transformation of the strength components have the same template like this one. Okay. And with this one, then that's pretty much done. So let me convert into these notations. I want to arrange into, say, tau 1, tau 2, and tau 3, and 4, 5, 6, okay, and with prom. This is an expression in 3x3 matrix, and again, using our notation, we can pick the 6 independent from 3x3, arrange into the orders, a sequence like this one. That one simply is tau 1, 1 go here, 2, 2, and 3, 3, and 2, 3, and 1, 3, and 1, 2. We take such an order to arrange from 3x3 into a column vector. It will be easier for us for the follow-up calculation. Okay, nothing special, just for the calculation purpose. And this one will be equal to the big matrix. And let me label it. Should be 6, 1, 2, 3, 4, 5, and 6. Okay, do this one carefully. And then again, this one will be multiplied with the strength, corresponding strength, and sorry, the stress. Tau 11, Q2, 33, 12. Okay, basically that one. Basically this one in our notations, that is the Tau 1, 2, 3, 4, 5, 6. Okay, basically here I've adopted this 1, 2, 3, 4, 5, 6. Okay. So right now you can see how to transform from this information to here. So let me do this one, just do the first row once. So basically this one is our Tau 11. So Tau 11 equal to this one, right? Okay, I do it once. This is our prom. So this is Tau 1 prom. Tau 1 prom, this element, I'm going to fill out the first row. First row equal to this one. Basically this is our notation 1. And what is Q1? Q1 is 6. And what is Tau 1, 2? The same thing, this is Tau 6. And what's Tau 2, 2? That is our 2. Okay, so Tau 1 prom equal to those things, so fill out the numbers, and there's a 6 by 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Oops, too big. Anyhow. So this is C square multiplied with Tau 1, and CS multiplied with Tau 6, so this is CS, and CS multiplied with Tau, so there's a 2 CS, and then S squared multiplied with Tau 2, something like this. Good? Are you able to do it for the second one? For the second one is Tau 2 to prom. Tau 2 to prom. Tau 2 to prom basically is 2 by 2 element. So you look for is to transform that information into this table. We good? Okay, so let me fill out the whole things quickly. S squared, C squared, and minus 2CS, and this is 1, and C minus S, and S, and minus and C, and this is minus CS, CS, and cosine 2 theta. Then double check. Yeah, should be right. Good.
Looks a lot like the alignment example, except for those middle things.
From here to here, that will help us more kind of the calculation in terms of the mathematical. Okay. So, which means from here, I can erase this one. How much time we have today? 5 minutes? Okay, we can do it. I can do it. So, which means from here, let me define the whole index is the Tau prime equal to, let me define the whole index is, sorry, using the capital C, okay, capital C, and let me define this one. This is transformation. This is T theta, and with Tau. Okay, so basically this defined is Tau. Okay, so that's a transformation matrix. The same symbol as we used in the previous sections. So now we have a transformation matrix, and then right now we talk about the StressStrain relation. Okay, in XYZ coordinate system, in XYZ prime coordinate system. So in XYZ, we have the relations can be like this. Tau. Okay, let me use this one. Tau equal to this. This is supposed to be stiffness matrix. Okay. And in terms of the terminology, this should be stiffness matrix. But for some reasons, my lecture notes still use C. So not to help me not to screw up for the remaining, let me use C, okay? But you know the meaning. So C is a meaning this matrix with epsilon. So let me write here. In a similar way, we have the relation between the stress and the strain. Right now, we have a stress strain in the new crown. That means description in the new corner system. Okay, and we come to the point. For the system to be symmetric, for the material to be symmetric, if you recall our definition, that means the relation must be invariant. The relation must be the same to be symmetric. So that means whatever we use here, that should be equal to that information here. That is to be, we call this material is symmetric. That means material constants, material properties are the same. Doesn't matter in which corner system you describe, right? Okay, keep this in mind. Then right now I want to relate the two words. And from this word, in this way, from our calculation, tau prime equal to T theta times tau. This one equal to T theta with this one. So again, the same as we did before. Let me do this one together. So that means T tau equal to C T epsilon. T is not singular, so inverse C T tau. That means these numbers must be equal to this number, right? Because right now we compare the same thing. So therefore here we achieve is the C equal to T inverse CT. That means this T transpose times C equal to C times T transpose. Like this, right? This equation must satisfy, doesn't matter how we change the value of theta. This result is obtained by claiming this. Where is this result is obtained by claiming we have used the same description here and here. Why we use the same description here and there? This C basically representing its material properties. Material properties must be the same under the assumption of symmetry. Okay, so based upon the argument of the material symmetry, we have this one. So to be proven for isotropic that we claim for all the value of the theta, this equality must be there. Okay, unconditionally for any value of the theta. Good. From this point onward, it will allow us to look into the content of the C. What would be the content? What means the C is right now the 6x6 elements, 36 elements. Using this one, we fully expand these equations. We fully expand this equation that will allow us to look into the condition for each of the 36 elements. What condition for each of the elements must be satisfied to make this equality hold? Okay. Understanding the logic? Okay. The handouts today I give to you, and that is my calculations, my work on this one. Basically, it's not my work, my exercise on this one, okay? So basically here, only one single point, and you need to adopt is this. To asking for this equality to be held, for all the elements. So as long as in that single equation, if that single equation involved with multiplication of sine or cosine theta, you make that term equal to 0. Then that will give you the contents. One example I'm saying is this. Okay, so right now out of the 6 by 6 element, I look for the 1, 1 element. Okay, the 1, 1 element. The 1, 1 element is this one. I look for this element. Okay, so that equation expanding just like the handout I give to you. The left-hand side expanded is c squared times c11 plus s squared c21 plus 2cs c61. Right-hand side equal to c squared. Sorry, the c squared 611 plus s squared c12 minus cs c16. Okay. When I look at the first element, the expanding will be like this. So compare the both sides. This term can be cancelled. This term and this term can be cancelled. C, in our definition, C is cosine theta. S is a sine theta. This again. So to make the whole things equal, to make this side equal regardless of the value of the theta, the best way is simply to make C61 equal to 0 and make the C16 equal to 0. If this coefficient becomes 0, then it doesn't matter how the theta change, we will make the equality holding there. So that's the key. So in this way, C16 is 1. So that means here, at least this element, that